Hi, hello, good morning. My name is Nico van der Kolk, and I'm excited to be here at the InnovSale 2020 and for the chance to present some of our work. This is actually the final work from my PhD research at the TU Delft, where I've been working within the Wind Assist research group under Lex Koning for the last years. And yeah, this is a piece that I've done together with a good friend of mine and colleague, Brian Freeman from Lakes Environmental Software. And he contributes, say, the machine learning expertise, which we've say plugged into the specific application of hydromechanic modeling for sailing commercial ships. So I guess you're all familiar with wind assist in the meantime, but the basic idea is to replace main engine power with wind assist power. Here in the images, you have several examples of technology which is, well, I would say, ready for market today. And I think even many of the representatives from these companies are in the audience today. This is a hybrid ship, so you have to consider wind assist, the contribution of wind assist against implications for the main engine machinery, for example, and an increase in ship resistance. So this is expressed like so as a P-WASP, which you may recognize from the EEDI formula. The term delta R sailing, however, does not appear in this IMO formula. And this is, in fact, you could say the main topic for my own research. On the right-hand side, this quantity P-WASP is presented for a small coaster. I think the installed power was 1.3 megawatts. So you can see that, in fact, there are some areas for full sailing is possible. Now, what I said that this change in R due to sailing is not in the EEDI formula. Um, that's because the EEDI formula is a 1 degree of freedom model and doesn't consider these constraints. On the other hand, P rotor, that is the energy required to rotate the device, the Flettner rotor, that is considered. So what happens when a large sailboat moves through the water? Yeah, there has to be a balance in the transverse direction. So there will be a heeling force next to an aerodynamic thrust. And then as a result, the ship will adopt a heeling angle and a leeway angle. So here you have 10 degrees heel in the image and 5 degrees leeway. The viewpoint, by the way, is from beneath the ship. So that's the normal ship maneuvering coordinates or hydromechanic coordinates. At the bow, you have a quite distinct pressure peak, which is associated with the linear lift coefficient. And then farther aft along the ship, you can see evidence for the Monk moment. Um, Finally, a vessel heeling angle will bring the shoulders of the ship fore and aft closer to the free surface, which will lead to let's say, expansion or contraction in the flow field and an increase in wave-making resistance. So the resistance of a ship, which has a normal Froude number dependency, in the case of wind assist also depends on the heeling angle and the leeway angle. This result here is from a Rance CFD calculation, a full scale um, with logarithmic boundary layer law for one of the hulls of the Delft Wind Assist series. That's one of the main products of my own research at the university. This is composed of three sub-series: a general cargo ship in red here on the scatter plot, Deadrise series, which is based on, say, the last sailing ships of the former century. And then finally, a low CP series, which would be representative of RoPax or a cruise ship. And then, of course, this is ongoing development. So yeah, we're, for example, now working on a low draft to length ratio ship, which would be representative for a deep sea freighter. The simulation matrix is a normal drift and heel sweep, which was 25 runs for the majority of the hulls. A full matrix would have been approximately 60 runs. This nominal matrix of 25 already took 100 hours using the RANS package and the HPC facility. Now, artificial neural network architecture, for those of you who aren't familiar, this is, say, the canonical units, the neuron. You have a series of input values, x1 through xn, and they each have a weight, which is approximately the coefficient from the regression formula. Then there are some step functions, so you can switch nodes on and off. It's the sigmoid. And yeah, these can be arranged into layers, so input layers, hidden layers, and output layers. And yeah, essentially this different nodes interact with each other according to the weights. So it's, you could say, an elaborated regression formula, or universal approximator. That's what it's often called. And the notion is, or the idea, there's a proof, I believe, that any continuous function can be replicated in this way. So the model setup, there's an important distinction to make between observations and features in the training data. So an observation would be, for example, a one ship speed, one ship hull, leeway angle, and beta, so a combination of operating conditions. On the other hand, features are, say, the information within the observation itself. In the case of a RAND CFD run, you're talking, well, for normal matrix, or sorry, mesh, it was about 7 million cells. So in principle, there are 3 velocity components and a pressure in each of these cell centers. For this initial work, we're working, say, with body forces, so the resistance, side force, and yawing moment on the ship. And that is because there's sort of a ratio between observations and features which you need to respect in order to properly train a network. And actually, the number of observations that we have available, which is 1,500, as you see here, is not so many for a typical machine learning application. So the training and testing split was 85-15. And you can see here on the figure on the right, which I've tried to modify to make a, say, logarithmic axis, that in the first 20 epochs, the training accuracy is already better than 90%. And then, well, the total training took something like 2 hours. And that's actually a bit misleading because, in fact, most of the work was data curation before this, say, Keras library could understand the data. The error for an artificial neural network is presented in terms of a mean absolute percent error, which is approximately a relative difference. And then, yeah, especially for the yawing moments, as you can see also here in the plot, that, yeah, if the correlation is perfect, then you should have a straight line. This is for the complete set of data, by the way. But that indeed, the yaw moment appears to show some deviation. One possible remedy and something we're looking into is training separate models for the different series. Because in fact, the low CP series and the dead-rise series don't share much in common. Yeah, and so in general, the uncertainties, the uncertainties are approximately commensurate with the underlying validation level for the RANS data. And next to that, the comparison error, in fact. So if you look here, this is an example of, say, a validation case. We have the hull number 1 from the series, so that's simply the parent hull. Blue is the CFD result, and black is the neural network result. And then here there are some maneuvering coefficients, as typically done for ship maneuvering, with corresponding uncertainties for the data, so not for the coefficient. However, the comparison error for these coefficients themselves is on the same order. Be cautious here, because in fact, fitting these maneuvering models to a limited number of, say, leeway angles, for example, introduces, you have quite a penalty for the uncertainty if you have a third order model and only 7 points. So this is promising, and we will continue. To conclude, yeah, this tool is apparently efficient and accurate. Yeah, if you really work out the comparison in computation time, then the processing time using a trained network is about 200 million times faster than a RAND CFD simulation. And it offers the possibility of the same caramba, the same level of detail and fidelity in the flow field. The validation uncertainties, the RAND CFD validation level, and the model error were similar. And this is actually a subject of ongoing work because I reckon there's quite some uh, uh, refinement which is possible in terms of the propagation of uncertainties and errors, also in the larger modeling context. Then, as I alluded to before, it may be possible to reconstruct flow fields. So you have, as an example, the wake fraction at the propeller disk. Next to that, say the angle of attack for an appendage. And here, the ratio of observations to features is the limiting factor. So in that respect, we're working on further series, so a low T over L series, for example, and adding more hulls to the existing series. Well, thank you very much, and I look forward to fielding your questions. And I expect Brian should be here online as well. Thank you.